Hello, firstly, I'd like to thank you for listening to my talk today. My name is Catherine Spuren. I'm a PhD student from Imperial College London, and today I wish to discuss the recent experimental work we did where we observed the distinct pore-scale dynamics that occurred from the transition to transient to steady-state subsurface multiphase flow, with these experiments conducted at the Swiss light source synchrotron. So, why are we interested in the pore-scale dynamics that occur during transient and steady-state flow in the subsurface? So, transient pore-scale dynamics are assumed to occur relatively rapidly to macroscale properties such as the pressure and saturation. Thus, transient flows such as the injection of CO2 into a reservoir are modeled with steady-state properties, and this is shown on the figure on the left. However, the underlying assumptions in this is that the pore-scale processes are the same for steady-state and unsteady-state flows, and that these fluids flow in connected pathways at steady-state. So the first thing we wanted to observe is, do fluids flow in connected pathways at steady-state? So for processes such as subsurface fluid flow and CO2 storage, what we want to do is predict the flow and the trapping using reservoir models. And these reservoir models have a number of key inputs, one being the capillary pressure and one being the relative permeability. But the assumptions in these models is that the fluids flow in continuously connected pathways. So what we've observed is that actually fluids don't always flow in continuously connected pathways, and what we can see sometimes at steady state are these intermittent flow pathways where the non-wetting phase is periodically connecting and disconnecting, and this has been compared previously to the flow of cars at traffic lights. So the flow networks remain the same, but the flow isn't always continuous, i.e. when the traffic light is red. And what I show here on the left is on the y-axis the capillary number, and on the x-axis the viscosity ratio, which is just the ratio of the two fluid viscosities in the system. And for three typical scenarios, I have measured out the typical capillary number and mobility ratios expected in the subsurface. So you can see for the box labeled 1, which is for CO2 storage and natural gas production, we would expect to see these intermittent pathways at steady state. And even for conventional oil production in this box here, we might see some intermittency at steady state, but less so. And this intermittency at steady state just suggests that there's the possibility of further complexities during unsteady state flow, but these had never been captured before due to limitations in imaging speed. So this figure on the left was produced by observing time-averaged images acquired over 40 minutes, and an example of this image is shown here on the right. So for this scenario, the rock grains are transparent, the brine is shown in grey, the continuous areas of nitrogen are shown in blue, and areas where there was a change in the occupancy during the scan and therefore the regions were blurred are shown in green, and these are the intermittent pathways. So we can observe like the degree to which they have occurred, but we have never been able to actually observe the dynamics directly and this transition to the steady state, which we have finally been able to do. We did this by using 1-second synchrotron imaging at the Swiss light source, shown here on the left. And what we did, we had our sample, which is placed in the core holder here, which is also shown in the beamline, it would be here. The X-rays travel down the tube like this, go through our sample, and are detected by the camera here. So we put our sample in our core holder, we saturated it with brine, and then we simultaneously flowed through brine and nitrogen gas, and we imaged the core as the fluids within it approached steady state. And steady state was deduced by a pressure transducer connected across the sample. And the experiments I'm going to describe in this presentation today were all done in the capillary dominated regime with a capillary number on the order of 10 to the minus 7. So with this time-resolved imaging, we are able to capture the dynamics as the flow transitions from transient to steady state. So for this image, the flow is from top to bottom like this, and I will just play this video, and you can see that the gas in red propagates in these large bursts known as Haynes jumps as it travels across the sample. And at some point, it propagates across the field of view, And then after this, it can continue to fill the pore space as we still haven't reached steady state, as we only image the middle section of the sample. And this shows just the transition to steady state for the entire experiment. So on the left-hand side is a figure of the gas saturation on the y-axis in red, and the differential pressure across the sample on the y-axis but black. And on the x-axis is the time after injection in hours. So what we can see is that prior to percolation across the sample, the gas saturation is increasing quite rapidly. After percolation, the saturation still continues to increase, but at a slower rate. And then before steady state, we see that the saturation plateaus out. And what you can see as well is that the pressure drop across the sample is increasing, and then at steady state, it fluctuates about a mean, but overall it's not increasing. And these numbers on the left-hand side correspond to the images on the right. And so what you can see is that the gas is traveling across the sample in figures 1, 2, and 3. And the dynamics are very easy to observe, but I have just zoomed into a smaller section for images 4, 5, and 6 to show the formation and the destruction of an intermittent pathway. And this is what I'll discuss in more detail in the next slide. The dynamics we observe at steady state are much more subtle. So on the left, we have a video similar to the one before, where the gas is shown in red, the brine is shown in grey, and the rock grains are transparent in this case, and the flow is from top to bottom. And this video is actually plotted in real time. So each scan that lasts a second is plotted a second apart. And what you can see is that it doesn't look like a lot is going on because the dynamics are so subtle. But if I just speed up the video, you can see that actually a lot is occurring. And say, for example, in this area shown in yellow, we can see that there are times when it's connected across that region and times where it's disconnected. So for example, now it's disconnected, but actually the intermittent pathway causes a connection which will subsequently disconnect. And what this means is that although the intermittency is occurring in very small regions, the impact it can have on connectivity when it's connecting these regions is actually quite large. And this is shown on the figure on the right. So on the y-axis, we have the number of ganglia, the discrete number of ganglia per unit volume. And on the x-axis, we have the gas saturation. And I've split this graph into the 3 stages, which is the unsteady state stage before percolation has occurred, unsteady state after percolation has occurred, and steady state in red. And what you can see is that prior to percolation, what we see is a large increase in the gas saturation, but not at the expense of the number of ganglia. So that remains pretty constant. Once percolation has occurred, the gas saturation is changing much less rapidly, but we are optimizing the pathway post-percolation, and the number of ganglia is actually increasing. And then at steady state, what we see is a very narrow range in saturation. The saturation is actually fluctuating plus or minus 15% of the mean, but we see a huge range in the number of ganglia, so the impact this saturation is having on the connectivity of the fluids. And in this direction, actually, the number of ganglia is fluctuating plus or minus 70% of the mean. So it really is something that we have to consider in our models. And just because the dynamics are so subtle, I have this video which is the same as the larger one, but it is just a zoom in on a region that is 400 microns in height. So what we can see is that for this individual gas ganglia, it is connected across the ganglia right now. And what will happen is it disconnects and then it will reconnect again and then disconnect. And what we can see is that we have these very cyclic periods where it's connected and then it's disconnected, and these are the intermittent pathways that are causing this large fluctuation in the number of ganglia. So you can see here it's connected again, and then just as the video continues, you'll find that it's disconnected and then connects a further time. So what we can see here is that although this is subtle, this is a very zoomed in region that spans only a few pores, the cumulative effect of these intermittent pathways is actually very large on the dynamics that occur at the pore scale. And these dynamics are very important in the connectivity and the trapping of the gas. So now we have observed the differences between the transient stage and the steady state stage of the fluid flow. What we want to be able to do is quantify these differences, and this is shown on the graph on the left-hand side. So on the x-axis, we have the intermittent event size, which is quantified by the number of pores involved in the intermittent event. And on the y-axis, we have the number of events observed, and this is for a 30-minute imaging window. And we have this for 3 cases. First, in blue, is unsteady state 30 minutes after percolation. In green is steady state 1 hour after percolation. And red is steady state. And what you can see is that the steady state dynamics involve those large bursts, which I described as Haynes jumps, up to 35 pores in size. Whereas at steady state, most of the dynamics only involves 1 or 2 pores, and in a small amount of cases, 3 pores, but never larger than 3 pores. And this just emphasizes that point I made where although these intermittent pathways are very small, they are occurring in these key locations and they have this huge impact on the flow of the non-wetting phase. So if it is occurring in these key locations, what is the impact of these intermittent pathways on plume mobility? So we've seen this graph already. It has the gas saturation in red. The differential pressure across the core is in black on the y-axis, and then on the x-axis it has the time after injection in hours. And what we saw before is that the gas saturation increases, then percolation occurs, and then the rate of increase slows. And then what we see is that the saturation plateaus out long before the differential pressure does. And what this means is if the saturation is the same, but the pressure is lower, we actually have a higher mobility during the unsteady state phase than during steady state. So I've described these results that we observed, and that was for a nitrogen gas and brine injected simultaneously into a carbonate rock. And I just want to expand now the generality of our observations, and we did this by conducting further 3 experiments. So experiment number 1 here is for the experiments I've already described. Then we did a further 2 experiments using nitrogen gas and brine, but just at different capillary numbers. And then we did a final experiment, which is experiment number 4, where we resaturated the rock with brine and we reconducted the experiment, but instead of gas, we used nitrogen. And what we can see with these results is that these subsequent perturbations of gas, so experiments number 2 and 3, we saw a much quicker transition to steady state. So when you're first initiating the gas into the porous medium, the transition to steady state is quite slow. However, subsequent perturbations will be much quicker. And what we also observed is the transition to steady state is much quicker when no intermittency is expected under steady state. So because the viscosity of decane is much higher, we would actually expect less intermittent pathways at steady state. And what we observed in the data, so here is the gas saturation on the y-axis and also the differential pressure. And then on the x-axis is the time after injection in hours. And what we can see is that the differential pressure across the decane, across the sample for the decane experiments is increasing much more quickly, and then it plateaus out much earlier than it does for the first experiment shown in red. So what is the impact of our results on modeling of, say, CO2 storage in the subsurface? So on the left is the image I showed in the first slide, which is the current framework for modeling, where we just model the CO2 plume with the steady state properties. And on the right is actually what we think should occur. So we should model parts of the plume with unsteady state properties, which are markedly different, and the mobility is higher, which means the plume will travel faster than expected than if you just use the steady state properties. Now the question is, how much of the plume do I need to model with these unsteady state properties? And so as an order of magnitude estimate, what we did is we calculated how many pore volumes it took to achieve steady state in our experiment. And for the gas brine experiment described at the beginning, it took 180 pore volumes for steady state to occur, which means the front 3.6 meters of the plume would be modeled with unsteady state properties. And while this number might seem small, in cases like the Sleipner field in the North Sea Actually, there are a lot of mud rock layers, which means that each layer is very small, and therefore the impact that our results could have on modeling these areas is very significant. So I'd like to thank you for watching my talk today. This work is funded through the President's PhD Scholarship at Imperial and the Shell Digital Rocks Programme. I'd like to thank all my colleagues for their useful discussions and their help during these experiments. And for further information, this work is actually published online on these two links that you can click. And if you want to check out the videos again, they are all on my YouTube channel, which you can click on the link here. Thank you again for watching.